Okay, so let's talk some logistics. We got project 2, we've got homework 2 coming up. You have a little bit more breathing room than project 1, thankfully. But it is due in a couple weeks. We're going to be spending both today's discussion and next Friday's discussion, just kind of going through everything I think you guys will need to do both of them. As always, website is available. We're not running through any coding exercises this week, but the slides are there if you are so inclined. But yeah, those are the deadlines. As always, please be mindful of them. As you guys probably have realized by now, Majid is a bit of a stickler for getting those in on time. So please make sure that you have them in and done well before then. Let's see. And then just out of curiosity, do we have any refugees from section 1A? You can throw F in the chat for our boy Sajjad, moving on to bigger and better things. But yeah, thankfully nothing bad. But he's going to be graduating a little early. He's actually got some employment opportunities, and so because of that, he couldn't stay through the whole quarter. So he had to resign early. But it's in his case, it's good news, but unfortunate news for the rest of us. But yeah, so welcome all you 1A'ers. This is definitely going to be a step down for you all coming here, but we'll do the best we can. But yeah, let's see. Okay, so I mentioned this in the email this week. We are doing a meme contest. I feel like maybe we don't have a lot of exhibitionists in the group, but if you want to sort of, this is your time to shine off camera. And let's face it, it is every parent's dream that their kid becomes a meme. That is really all we can hope for in today's day and age. So I have the photo here that I would like you all to create memes for, and then I'm going to throw the direct link for it up in the chat as well. So here is your mission. Let me know if this works. Here is your mission. Oh, not yet. Download it. Come up with the best caption you can, because Lord knows you are all following this lecture with rapt and undivided attention and would never dream of zoning out or doing anything else. But you're going to come up with the best caption, shoot me an email, and then at the end of lecture, I'm going to take all the submissions, I'm going to throw it up on this deck. We're going to review it collectively, and then we're going to vote, just like we always do every week. And yeah, we're going to just see, winner takes home the glory and the Starbucks. So hit me with your best stuff. One other kind of quick item for us to discuss. So as you know, this course is wrapping things up early. I think we're done with material, I want to say by week 9 or something. I'm not sure when the exact final deadlines are, but certainly by week 10, your last stuff comes due. So there's kind of this open-ended question of what we actually want to do week 10. If anything, it's your time. So, I did want to kind of throw that out there and see, we don't have to come to a decision as discussion now, but at least kind of just start thinking about it. Possible options for you. The most obvious and the lazy bum in me is like, let's just cancel it. That would be great. And then I don't have to, sit here and prepare stuff for 2 hours, which would be awesome. And not an unreasonable thing, given that you have other courses, other, finals to prepare for. So if you want to just cancel it, we can go ahead and cancel it. There are other sort of miscellaneous things within the course. I think we cover so much material and throw it at you so quickly that maybe we may want to use the time to kind of circle back and talk about maybe some other stuff. So, if there are any sort of specific topics that we just kind of glanced over and were like, hang on, like, I kind of want to talk a bit more about that. We could totally prepare some material for that. Maybe even just kind of walk through some specific data science projects. I think Majid is planning on doing that as well at the end of the course, but that could also be something we could do. We could also do just something just completely random. So, uh, when we taught this last quarter, we ended up having a conversation about career advice. So I know, like, a lot of the UCLA doesn't really provide a lot of career guidance, everything from job placement, networking, things like that. So I think most of you guys kind of have a sense that I'm coming from a little bit of a non-traditional background here. I'm a little bit older than your typical grad student. I've been working in industry now for a decade. This is actually my second go around in grad school. So, I guess I have a little bit more of kind of experience in terms of that, and maybe we can talk a little bit about that. And then, to be honest, there isn't a whole lot of things in this world I feel particularly confident talking to a bunch of y'all for 2 hours about, but I do have degrees in economics and philosophy, and I have a master's in healthcare policy, so I could totally talk about that. And then I don't have a degree in it, but I did take courses in screenwriting, and my wife is a filmmaker. And I think my one claim to fame in the CS department is I think I have the most impressive IMDb page in the whole CS department. I'm otherwise a thoroughly unimpressive grad student, but that's like the one thing I have going for me. So, if you ever want to talk screenwriting, if any of you want to feel burned out on CS and just want to pursue the Hollywood dream, we can totally do that. So yeah, so let me know. I'm seeing in the chat some people talking about like the type of research we do in the lab. We can totally talk about that. Yeah, so just let me know. We don't have to settle on anything now, but yeah, I'm not gonna lie. It's not gonna happen. I mean, I'm not gonna say it's not gonna happen, but it would totally be a dream to literally just talk about screenwriting for 2 hours. Like that would be, I think, so much fun. I don't think I can get away with that, but if y'all are particularly passionate about that, that would be fun. That would be a lot of fun to do, but I don't know if we can do that. But hey, I mean, they are trying to build algorithmic approaches to screenwriting now. Always every few years a couple of years ago, they even produced a film that was auto-generated using natural language generation. It was terrible, but like they all keep trying it. So there's some tie-ins there. So let me know. We can do that. Savannah has to make a special appearance. Yeah. So yeah, week 10, we'll maybe I'll put it up to a vote or something, and we can kind of settle on a topic for that. But just wanted to float those out there. Let me know what you guys are feeling. Okay, so let me pause there before we dive in. Does anyone have any, I guess, logistical questions or just anything before we kind of dive into material for the week?
Why not? Can you put your website link?
Oh yeah. Sorry about that. Here, okay, it's right here. Oh, maybe I can just put that in the copy link. Let me put that in the chat too, so you guys don't have to painstakingly type that. Oh, okay. Rohit already did that. Awesome. Thank you, man. Yeah, so it is in the chat. Any other questions? So my wife is a filmmaker, so she primarily works directing and producing, but I mean, when you work as an independent filmmaker, you kind of wear a lot of hats. So she's done a lot of editing jobs. She's done casting. She's done work in front of the camera too, acting. I mean, you kind of wear all those hats. She has a degree in entertainment industry management as well. So she consults with, I mean, she just does a lot. But yeah. Okay. Let's see. Oh, so you're asking, it's such a big industry. I very much doubt she's worked with anyone in particular, but yeah, any other questions, I guess, about really anything before we dive in? Okay, so out of curiosity, how many of you have started on project 2? Like show of hands of the, okay, I'm seeing some hand raised, I'm seeing a lot of no's, kind of a balance thing. Most of you just looked at the deadline and was like, that's not due until next month. I'm not going to bother. See, that's the thing about like when you give, I think there's like a sweet spot about assigning things where you want it, if you give people too much time to get something, they take one look at it and they're just like, "Oh, I'll worry about that later," and then they never get it done. So I actually think there's like an optimal scheduling thing where you give them enough time that they're not crazy busy, but not so long that they're like, whatever, I'll deal with it later. I don't quite know what that balance is, but I think in this course we're going to opposite extremes. It's either like it's due tomorrow or it's due in a month. We kind of need to work on our timing, but we'll figure it out. But okay, so for those of you who haven't gone through it, I'm going to go through some of the key kind of concepts that you need for project 2, both this week and next week, and then the homework is pretty much aligned with the project conceptually. So they should pretty much go hand in hand. The homework in particular, I don't think is overly challenging. I got a hand in terms of doing it, so I think we can. That should be pretty easy to knock out. And the project 2, like we talked about, you've already done the vast majority of the coding for this class that you need in project 1. So you can port over most of that. There's just going to be like a few specific things, and we'll walk through them both this week and next week that you would need to get it done. But again, the challenge for this project is not going to be coding. We're going to pretty much, between the coding examples, everything else, we're going to pretty much give you everything you need. It's really just about starting to think about sort of the conceptual aspects of what you're doing. That's really what we're trying to get into with this project. And so for those of you who haven't looked at it yet, the big thing with this one is we're shifting from a predicting model to a classification model. And so prediction is you predict a value sort of a continuous variable, whereas a classification is you are choosing one of a discrete set of classes. It can be, in this case, we're doing a binary classifier. So it's either a yes or a no, or in this case, a sick or non-sick. So you're given a data set of patients with certain health conditions, and then there's a sort of an associated label of do they have, I believe it's heart disease or not, and your job is based on that data to try and classify the person. So a patient who presents with certain symptoms, certain test results, can you classify whether or not they have that condition? So that's at sort of a high level what we're looking at. And the project is going to kind of walk you through a number of different things. So the first thing that we do, we mentioned, is we sort of we had talked previously about how important it was to scale your data. And why, for certain classifiers that can be incredibly important. And then we just kind of showcase that this time. So we have you run specifically a KNN, which, because it uses geometric distance, it's highly sensitive to the relative magnitude of each feature, of each dimension. And so because of that, we have you just plug in your essentially raw data into a KNN model, and then we say, okay, well then pipeline it and then plug that, basically that exact same data in, and look at what a difference it is. And then partially that's to show the impact of scaling, but partially it's just to show how important that data engineering step can be. And I know in previous discussions, we've spent a lot of time talking about that, but like how you can frame certain features, how you can kind of model the relationship between a feature and a label, and thinking through that, and just how important that can be in terms of impacting performance of your feature. So we want you to look at that. We also want to kind of get you playing with parameter tuning. And we're going to spend a lot of time over the next few weeks talking about those parameters. So things like different solver models, different gradient descent models, different normalization options that you can take. For K, they're going to be specifically, we're going to ask you to tweak the number of nearest neighbors. So, because the K in K and N just stands for the number of nearest neighbors that you take, and how you can sort of optimize the results of your model around those various parameters. So we ask you to look at that. And then the other big thing, and we're going to spend, I think the bulk of today's lecture talking about this, is metrics. We had talked previously about metrics for regression, how, man, I should have put up like at least a meme or something, because this is just boring. You're just staring at balancing a data set for 20 minutes. But we had talked about predictive regression metrics previously. So we had talked about like things like MSE, MAE, RMSE, and like some of the differences with those. We're going to look at metrics specifically around classification, because as we had sort of hinted at last Friday, there's a difference, right? When you're dealing with a prediction, the relative magnitude of that error matters. And it's not sort of an obvious you got it right or wrong, but it's really a how close did you get it. With classification, it's more obvious if you got it right or wrong, right? If you have a discrete set of classes, you are sick or healthy, and you predict sick and the answer is healthy, there's a very obvious right or wrong there. So the way we think about errors, the way we think about that is different. But even within that, and we kind of teased up that topic last week, we talked about false positives, false negatives, thinking about certain types of errors and why it could be the case that not all errors are treated the same. So we're going to talk a little bit about that. And then we're going to talk, I think finally today, we're going to talk about a concept called cross-validation, which I know Professor talked about in lecture, but we're going to kind of talk about that again in this discussion as well, just to kind of hopefully reinforce that topic and make it good. But so that's our plan in a nutshell. Only took me 20 minutes to get there. But first topic I want to tee up for you is balancing a data set. So get in some Marvel Cinematic Universe, which, let's be honest, I don't pull enough memes from the MCU, and I really should be. But so I have this quote here. I actually pulled this directly from a Stack Overflow question. It says, I have a binary classification problem. One class is present with a 60-to-1 ratio in my training set. I used a logistic regression classifier, and the result is it just seems to ignore one class. And so basically it's saying I have this label that just happens to be highly skewed to the degree of a 60-to-1 ratio. I looked at, I ran my model, and it just seems like it's just completely ignoring that. And it's just uniformly predicting the other one. Well, if your goal is to maximize accuracy, that's kind of makes sense why that might be, right? If you're getting 60 right for everyone you get wrong, I don't even know what that ratio works into, but that's a pretty damn high accuracy score. So, and this kind of leads into part of the problems we get with accuracy as a metric. And we're going to kind of circle back on this. We're going to talk about this a bit more once we've teed up everything else. But this is a pretty persistent problem that you're going to get with almost any data set that you work with, is that you will almost always have imbalanced data. And the problem with using accuracy, because accuracy, so we're going to get into a formal definition of accuracy, but, oh, okay. Daniel's got a score. Okay, yeah, 98.3 accuracy, like holy cow, right? Thank you for doing the math on that. Yeah, like that's a fantastic accuracy score, right? You look at it and you're like, okay, I can go home. That's great. 98%, like, I can publish that, get my thesis done, boom, I'm good to go, right? But the problem with accuracy as a thing is that it just looks at the overall number that you got right. And when you're looking at an imbalanced class, for instance, something like this, it ignores the type of the error. And we will talk about a little bit more about kind of issues with your data and how to handle that. But in sort of real life, chances are you're going to deal with imbalanced data sets. And so a classic example of this might be something like fraud. So I don't know how many of you have gotten those UCLA emails. Your data is now floating around the dark web. Has that been y'all
I
getting?
did. Rough times.
Oh, I'm sorry, Akshay. Oh man, I'm sorry, guys. I haven't gotten the email yet, but I feel like it's only a matter of time. Yeah, just as an aside, if you have not frozen your credit, it's a good idea to do so. It's really easy, really simple to do. I don't even think it costs anything anymore. Back when I initially did it, I did it. But yeah, just as a side, do freeze. Just it's a good it's just a good practice to do to freeze your credit. And essentially what happened, I don't know if do you guys know what it means to freeze your credit and all that jazz? Does anyone want to talk about that? Or are you guys good?
I'm interested.
Okay, so in really brief, so every time you apply for something, every time you kind of go through sort of a formal application, whether it's for a loan or to purchase something or anything like that, they run a credit check. They run your background check. They'll take your social security number, and they'll do it. And there are these crediting agencies. So there are three of them: TransUnion, Experian, and Equifax. And they will run your background, and essentially your credit history is just kind of an accumulation of all of your financial history, and it's generally used as a gauge to say how trustworthy, how reliable you are in terms of everything. So it'll impact everything from like whether or not you'll even get approved for certain financing, whether or not you'll how favorable your rates will be, everything like that. So it does matter. If you freeze your credit through these agencies, it effectively prevents anybody from running a check on you. So let's say I steal Daniel's SSN and I'm like, ha ha ha, I will go to the bank and take out a massive loan and pretend to be Daniel. So they're going to ask for his information. I'll be like, okay, I will just give you, my name is Daniel and here's my SSN. They will run it and they will not be able to run it because it's frozen. And so it's just kind of like an added step. If you then actually do want to apply for something legitimately, you would just go to those credit agencies and unfreeze your credit scores as needed. And I mean, the reality is you will probably only need those, a handful of times. I mean, basically, unless you're applying for a credit card, an auto loan, a mortgage, maybe some employers will ask for background credit checks, but some rental applications may ask for that too. But the reality is at most you're doing that once a year, probably. So yeah, so the reason if somebody has your SSN, that's not enough to do it because it's a separate process. It's a separate code to do it. So just having your SSN doesn't enable you to unfreeze your credit. You need separate credentials to do it. So it's kind of an added security thing. So it basically says, even in the event that your SSN is compromised, there isn't really anything that anybody can do with it. Well, I shouldn't say anything people can do with it, but they can't take out massive loans in your name or things like that. So it's just in general, whether or not you were compromised this particular time, it's just good standard practice to do. So yeah, if you haven't done it, I highly recommend to do it. Again, I think it's free. It's a simple process, and then it's just an added benefit. But do in general have credit monitoring. Do in general have those things. These things do matter, and they can really mess up your financial future if somebody does compromise it. So, but back to data science. So financial fraud is an obvious example of something where we might want to build a predictive model, right? Let's say you are Visa, MasterCard, you're processing all these payments. Gee, wouldn't it be great if you could predict potentially erroneous charges? And I'm sure you've all gotten these, right? I'm sure, there are times when there have been suspicious activity on your card and it'll get flagged and maybe your card will kind of like auto lock until you confirm those things. Have any of you gotten that experience? I'm getting at least one yes. Oh yeah, okay, cool. I'm getting a couple of yeses. Yeah, so there's a huge, talk about like applications of data science. Like there's a huge sort of cottage industry around just trying to predict fraud and looking at sort of fraudulent transaction types and building predictive models around that. The thing about models like that is they're very statistically sort of long tail events. I forget what the incidence of fraud rate is, but you know, if you're something like Visa, MasterCard, like you're processing literally billions of payments a day. And that is, you know, something where I think I saw something like it's on the order of 0.03 or 0.003, like some dramatically small fraction of total payment volume is fraudulent. And maybe if any of you want to Google that and throw that up in the chat, that would be cool to get that stat. But the point is, it's, you know, it's a very long tail event, and you can very easily create a classifier, just like this one instance here, that looks at total payment volume and says, hey, I'm going to get, I'm just going to predict everything as being accurate, and I'm going to get a 99.99% accuracy. And look at that, you know, my job is done. Well, obviously it's not. But that's an example about where minority class classification is hugely important. Because what we really want there is we don't want something that's 99.9% accurate with overall payments. We want something that of the fraudulent ones, it's grabbing, you know, the vast majority of those, right? That's really what we care about. And so we're going to talk about some metrics in a moment that are going to look at kind of alternatives to accuracy that would focus specifically on those types of problems. But just to kind of level set about that, you know, understanding sort of that balance in your data set is going to be a problem. And, you know, let me just say this, it's a problem when you're training your model as well. You know, so as a kind of as a general rule, when is a feature imbalanced? There isn't a good hard and fast rule. What I've seen out there is a 4-to-1 ratio. If you're, you know, if you're greater than 4-to-1 in terms of your imbalance, in terms of your labels, generally speaking, you would consider that imbalanced. So let me just pause there, just kind of throw up for some questions. Do people have any questions specifically about balance and imbalance in a data set? Okay, so we'll talk a little bit more about this in a moment, just to put a little more context on, but let's talk a little bit about how you might handle it. I put some things out there, just sort of to some strategies you might take to deal with a heavily imbalanced thing. The first is a downsampling approach that says, like, if you have a high volume of data, more than you would reasonably want to use for your model, well, then you can simply select a subset that just happens to be more proportionate to what you would like to do. The flip side of this is you can also augment. So, you know, we talked about augmenting columns, augmenting rows, right? Creating synthetic data. And this is something we also do, particularly when we're dealing with much smaller data sets, where you can try to augment your data set with additional samples of your minority class to try and, again, kind of balance that out. The final thing is weight balancing. So, you know, we can change sort of our loss function to prioritize certain pairs. And I'm going to kind of take a pause there on the whole concept of a loss function, because that is something we're going to get into. That's the mechanics of how your model learns, how it kind of scores itself, right? We sort of said like, oh, well, to date we were like, oh yeah, well, I'm going to train a model and it's going to produce this optimal result, but we haven't really talked about the mechanics of how that works. We will. But I just kind of want to just throw that out there. Let's see. So,
a quick question.
Yeah, please.
In relation to the 4-to-1 ratio, is that like the feature that's imbalanced has a 4-to-1 ratio with the next highest feature, or with all features? Like what are you comparing?
Oh, okay. Yeah, sorry. Great question. So that's within itself. So that's if you think about the values within a feature. And specifically, we often are less interested in the values of the feature, although we could be, but more about the label itself. So if you're thinking about like in on project 2, healthy to sick, if the ratio of healthy to sick is 4-to-1, then we might say, okay, that's an imbalanced feature. But yeah, you're looking at specifically the values within a feature.
Okay, thanks.
Yeah, absolutely.
Is that for a binary? Is that for a binary classification?
Okay, so yeah, okay, so great question. Was that I didn't see who asked that, but yeah, so it could be binary. It could be a multi-class classifier in which you have just a so I can give you an example of this. We did a study where we were trying to predict a relative magnitude of mental distress, mental sort of health on a particular given day. And we had, so that was, we were looking at a multi-class classifier where we had labels for healthy, we had sort of low stress, medium, and high stress days. And so, but the not necessarily a problem, but for our data set, we had, we had a high number of no stress, a relatively decent amount of low stress, and then we had only a handful of medium stress. I think we had like 2 high stress. And so that was an example of where within a multi-class classifier model, we had so few examples of a particular class that we weren't able to really do an effective classification on that. So we did try to do, in that case, we tried to augment that particular one, but we honestly had so few samples that even just trying to do like a statistical augmentation didn't work. What we ended up doing in that instance was we actually sort of collapsed our sort of mental distress days down to a binary classifier. So it was a healthy or unhealthy thing. And that was the approach we ultimately took for that particular one. But so you can have this, so to your question, we can do this for a multi-class one as well, where you need to have a sufficient volume of each particular label that you want to classify for, but it can also be for a binary classifier. So again, the healthy sick thing as well.
And the other thing is when you have augmenting data, when you're augmenting your data set, how does that give more information to your model? Because you're creating fake data off of your old data, so that doesn't seem like you're adding any new information.
Yeah. Okay. So great question. So, so you're right to say that you're not necessarily adding. You potentially are adding a little bit, because generally what you do is you're not replicating points precisely. You'll do something like a bootstrapping method where you'll take sort of a statistical sampling, and so you will generate sort of estimated data points within a data distribution. So you do give your model a little bit more variance with which to classify, but the main reason that you do that you would do that is twofold. The first is you're trying to balance the scoring of it. So you get away from this, something like that 60-to-1 ratio thing where it says, well, I can just ignore this because I never have to predict this because its impact on my optimization is so minimal. So by throwing more of those in there, you effectively sort of teach it not to ignore the class. The other reason it's important is you also teach it not to learn a specific pattern. And this gets into a question of overfitting, where if I have only 1 or 2 instances of a particular label, it might say, well, rather than learning some generic pattern associated with it, learn those specific values. So i.e. if A, then B. So if I see this particular permutation, return this class. Otherwise, don't do that. And that's not really what we want. We want it to learn a pattern. And so by doing something that's sort of more of a statistical distribution, you enable it to kind of learn, hopefully, to learn the broader pattern associated with it. But yeah, great questions. But that's generally what you would hope to accomplish by an augmentation strategy. Because you're right, you're not necessarily feeding it new information that it wouldn't otherwise have. No. Any other questions around this?
Yeah, I guess I have a small question about that. Are there times where your data set might not be a good idea to augment it this way?
So there are a number of cases where it wouldn't necessarily make sense to do that. And so one example was the one I gave you before. Like if you literally have only 1 or 2 or only a handful of instances where generating any kind of statistical bootstrapping of it just isn't possible. That might be an example where, because you're not really fixing the problem in that instance. All you're doing is kind of teaching it again to learn that specific iteration, that specific pattern, and not learn sort of a more general model of your data. So that might be a reason for it if you can't get a sufficiently good statistical sampling of it. Another reason to do this, and this is another thing to be aware of more generally, is, and let me ask you this, should we aim for 50-50? Like, let's say we're doing a binary classifier. Should we aim for a 50-50 distribution of our labels? Why or why not? What do you guys think?
I would think no. I would think that you want it to model the real distribution of the data as close as possible.
Good. Okay, so Patrick, great point. So why do you think you'd want it to model the actual distribution of your data?
Because I don't know. I didn't really think it through.
Okay, no worries. Well, your instincts are exactly right. And this is another problem you can get into is something like this, which is that you can make your model overly sensitive. Where if you've trained your model to effectively expect a 50-50 sort of output for your things, it might sort of learn to be oversensitive. And what a disaster that would be, for instance, to take financial things. If you're looking for something that occurs 0.003% of the time, and you've trained a model to expect it to occur 50% of the time, what kind of performance is that going to look like? So you're absolutely right to say that while you may not, and this goes back to that whole thing about like, what is an appropriate thing? When is it appropriate to try and balance your data set? When is it maybe better not to necessarily deal with the overall ratio of your data, but change the way in which you balance your errors? And this is sort of a good example of that potential trade-off. It's sometimes better to do data balancing, and sometimes it's better just to change your loss function to say, you know what, I'm really, really going to care about this minority class, and you're going to optimize to make sure that you don't predict it wrong, even if it's a fraction of the overall number that you're going to classify. So, and I think that gets back to the previous question about like, when would it make sense to augment or not? That is part of this decision process. When it's important to you to maintain the overall ratio of your thing, but at the same time, you still want to make sure that the minority class is getting sort of accurately predicted for, you may want to take that approach. So again, and as with all things with data science, there almost never is an absolute right or an absolute wrong approach to this. It's just one of the things that you, as the data science formulating your solution, kind of have to think through that solution, think through that approach, and think through the way you want to approach this problem. So
a question about just the augment definition in general.
Yeah.
So it sounds more like augment in this case, we mean like bootstrapping, so that we kind of get that sort of random distribution of, or kind of like using the data that we already have to kind of create more.
Exactly.
But, so is this like is augmenting just in general? Because I think in like project 1, we created like new fields where we combine different features, or we could. So is that just kind of like a general definition of augmenting, just basically adding new data to the?
Yeah, so great question. I'm glad you asked to clarify that, Michael. So yeah, augmentation just means sort of expanding your data frame, and we've looked at it from both expanding your columns, so expanding the number of features, but then also you can think of augmenting precisely as the bootstrapping approach, expanding the rows. Yes. So both of which can be considered forms of augmentation. Yeah, great questions about this. Any other questions? Okay, onwards. Metrics. So I think that kind of teed up a good sort of framework for us to now think about sort of how we evaluate a classifying exercise. And I saw this sort of online, this visual representation, and I think it's a great way of kind of thinking about errors. So we're going to use this framework when we're talking about metrics going forward. So let me just kind of talk you through what it is we're looking at here, and then hopefully it'll kind of make it a little bit more intuitive what we're looking at and why. So in this case, everything, so this is our universe of data, and then everything within this circle should be positive. So everything within this circle should be positive, and everything outside of the circle should be negative. So those are your actual values, your actual positives and your actual negatives inside the circle and outside the circle. And then we divide it into these columns here based on our guesses. So this column here, if you're looking at it on the left, on your left is everything that you guess positive. And this column here is everything that you guess negative. Okay, so do you kind of have that frame of reference for what this is? And then within that, we kind of have our sort of data here. So in this case, this here is my true positive area because this is the actual positives, and this is what I've predicted as positive. So that's my true positive. And then this here is a false negative. So here I have predicted that it is positive, but it is in fact negative. So, was I false? Oh, sorry, I represented this wrong. I'm sorry, guys. I got this exactly the wrong. Okay. Rewind, ignore everything I said. I'm sorry. This column is everything that is positive. Okay, I'm sorry. Oh man, I took something that was super intuitive and I just messed it up. Okay, it's the exact opposite of what I was trying to say. This column here is everything that is positive. The universe of positive things are here. This column here is the universe of negatives. This circle is what we predict as positive. And then everything else is what we predict as negative. Okay, so I'm sorry, I got that completely screwed up. Okay, so then within here, this little quadrant here is actually positive, and I predicted it was positive. This quadrant here is actually negative because it's part of this column here, the negative thing, but because it's within the circle, I predicted that it was positive. So those are my false positives. Okay, and then conversely, all of these fields right over here, these should actually be positive. So I should have predicted them as positive, but I didn't. So those are false negatives. And then these here are true negatives. So here, these are actually negative, and I did not, and I predicted them as negative. So then these are true negatives. So, okay, I'm sorry. Does that make sense to everybody? Because I know I totally screwed up the explanation, but are you guys following in terms of what's what? Yeah, I'm going to take that stunned silence as a yes. So the first thing and the most basic metric for us is accuracy. And again, accuracy is just simply the fraction of predictions that your model gets right divided by the total number of predictions. So in this case, the fraction that I get right is the true positives and the true negatives, right? Those are the ones that I predicted positive and they are positive, and the ones I predict negative and are negative. So it's true positive plus true negative divided by everything. So that's true positive, false negative, true negative. So that's accuracy. That's our most intuitive thing. And again, as we discussed, in an instance where negatives sort of vastly outnumber positives, this is not a great metric for us. And we'll kind of reassess that. Here's another model that kind of gets specifically into minority classes, and I think is something that we're going to look at, and that's precision. So precision says for every guess I take, how many guesses do I get right? So every time I shoot my shot, what's my scoring percentage? And so in this case, it's simply right. So if you look at this thing, its precision is remember, if our circle is the total number of guesses that we've taken, we look at what ratio of those guesses that I've made are accurate to the total number of guesses. So again, looking at here, if this is my total number of guesses here, I look at what my actual positives are divided by the total number of positives that I've guessed. So precision in this case is simply true positive divided by true positive plus false positive. And remember, this is something, so we talked about last time, sort of those type 1 errors, those false positive things. And we talked about, if you guys will remember specifically, we talked about like the criminal justice system and saying, you know, sometimes we're really, really concerned about those false positives, about predicting that saying somebody is guilty when they really aren't. If you guys remember that. So precision is precisely the kind of metric that looks at those instances and says, you know, we really, you know, maybe it's okay if we miss a bunch of actual positives. So going back here, maybe it's okay that all of these positives that we should have been getting, we don't get, but we just really want to make sure if we make a prediction, we're predicting, you know, we have confidence that we're predicting correctly. So that's what precision looks like. Recall is the exact opposite. So here it's the idea of saying, okay, if I'm casting out a net, if my model is trying to grab all the instances of something, what total percentage of those instances is it getting? So here, if here we were looking at the number I get right over the total number I make, here I'm looking at the total number that I get right divided by the total number I should have predicted. So going back to here, if this is my total universe of positive classes, what is the percentage of those that I'm getting correctly? So again, it's true positives divided by true positive plus false negative. And again, this is that type 2 error. That's that false negative error. And we say, like, remember we talked about like medical diagnosis, like particularly for preliminary medical diagnostics. Like maybe, you know, if somebody's coming in for an initial screening for a disease, you may want to catch that. You may want to catch everything, even if there's a low percentage chance that they have that. If they do, like the last thing we want them doing is walking out of the hospital saying, I'm healthy, if there's even a chance that they're not, right? We want to flag it and maybe send them for follow-up testing to confirm a diagnosis. And so that's the idea here there. It says, you know, if there's something out there, if there's an actual positive out there, what is the percentage of those actual positives that I'm catching? And again, here the problem is the exact opposite. I don't really care how many negatives I'm getting there. I just want to make sure that if there is a positive out there, I'm not letting it sort of go away. So that's recall. So you may also want to take a more balanced approach to that. You may say, you know what? I generally want to look at both precision and recall, right? I want to make sure that if I'm making a prediction, I'm making it accurately. I'm not just predicting everybody. But at the same time, I also want to make sure that I'm getting as many of these as possible. So I may want a more balanced approach to those two, right, intuitively. And that's what an F1 score is. So an F1 score is just simply a balance of precision and recall. It's a weighted average of these two. Here's the formula specifically if you can mention it. So you multiply your recall and your precision score times 2, and then divide it by the sum of recall and precision. So I believe I think it's called the harmonic average of those. I don't know what it's a harmonic, but essentially that's sort of the weighted average of those two scores. And it essentially says when you really care about the minority class, harmonic mean. Yeah, Timothy, I think you're right. Yes, the harmonic mean of those. So when you really care, you care about the minority class, you care about sort of getting those positives, but you don't want to, bias either towards a type 1 or a type 2 error. This kind of allows you to get a more balanced approach to it. So, okay, before we get there, so any questions on those 4, accuracy, precision, recall, or F1 score? Because those are kind of your workhorses for classification.
I guess I know obviously it's dependent, but is there one in particular that you feel like is a go-to or typically like a good starting point, or typically performs the best?
Yeah, so we're going to have I'm going to have a slide specifically, okay, here, where I'm going to kind of talk through the balance of each of those. I'll just say that in general for now, most of the time F1 score is what we defer to. Because again, we feel like that's a more balanced look at both precision and recall, and it controls for class imbalances. So in general, when you're looking at the performance of a model, you will tend to defer to an F1 score. There are reasons why you wouldn't, but the majority of the time, I would say you use an F1 score.
A follow-up question that I have about the F1 score is, what kind of values can we expect to get, and what is like considered? Do you have an example of what's considered a good value to have?
Yeah, so for all of these scores, these are going to be proportions. So these are going to be ratios. So it's going to be a value between 0 and 1, with 1 obviously being perfect and 0 being just dreadful. And this gets back to the general question of like, what does success look like? And obviously, generally speaking, the closer to 1 you get, the better. But beyond that, I'll just to give you an example, in terms of things that we would consider publishable, generally speaking, if we're seeing like predictors in the upper 70s, low 80s, at that point we would say, okay, this is robust enough that we would publish on it. But again, it's very, very specific to the model that you're trying to do and what you're trying to accomplish. So just like with precision, right? Part of your job is to define what success looks like and what is an acceptable performance metric for your particular model. Yeah, great question. Any other questions on metrics? Okay, cool. So we will also, for project 2, ask you to generate a confusion matrix. And this is a really, really useful, really cool data technique for visualizing the type of errors that you make. So, and we talked about this before, there's a question like, I think in office hours, we were talking about like, what information does a histogram give you that maybe you couldn't get if you just pulled up statistics and things like that? And oftentimes there isn't, but but at the same time, it can kind of help you to understand your model's performance and help you to understand if there are errors being made, like how they're manifesting. So in this case, it's a 2-dimensional kind of grid where it doesn't have to be arrayed this way. It can be arrayed in any way, but like in this case, your true label is here, your predicted label is here, and then you look at the intersection between them. So in this case, this would be an example of cancer. So malignant, benign, malignant, benign. So here's the idea of like, this quadrant is where the actual label is malignant and you've predicted malignant. Whereas this one is the actual label is benign and you have predicted malignant. So quick pop quiz. If the actual label is benign and you have predicted malignant, what kind of error is that?
False positive.
False positive. Yes. Yes. Thank you, Daniel. Thank you, Dean, in the chat, and Jaquin in the chat. Oh, awesome. Okay. And then let's look at the opposite. So here, benign, you've predicted benign. You predict benign and it is malignant. By process of elimination, what would that one be? Obviously, it's a false negative. That's your type 2 error, right? Where it is, you falsely said it's negative, but it's actually positive. And again, I think the utility of something like a confusion matrix is not that you couldn't infer that data just by looking at precision and recall and getting those numbers, but it's just a very easy tool for you to kind of look at that and say, oh, hey, my model is performing well, but for some reason it's generating a lot of false negatives. Maybe I need to do something about that, or vice versa. So it's just a really easy visualizing tool to just kind of see not just what errors are being made, but where they're being made, and just kind of understanding those distributions. So just a really useful thing there. Okay, let me jump ahead for just a second here. let's talk about how to code these. Yeah, so let's talk about, so I in the coding example that we went through, I mentioned that scikit-learn, sklearn has a metrics library that you can import. And within that, they have accuracy score, precision score, recall score, F1 score. And so all you need to do to generate those numbers once you've generated your model is just like with everything, you just call those particular ones, you generate, and do it based on, so here, or if you'll recall, just using our lexicon, predicted in this case is the set of labels that you, for your testing data, you plug in your testing data, you generate a set of predicted labels for it, and then those are your actual labels. So actual label, your predicted label, and you'll generate a accuracy score, precision, recall, and F1. And again, easy, trivial for you to do those things. If you can generate accuracy, you just swap out the particular one, you get all of these other ones. And then again, to your question, kind of here's sort of an interesting example of this, where like we look at the, this is just an example, but the accuracy is 76, so that's not great, that's not terrible, but interesting enough, we see our precision score is really high. We have a 92% for that one. So that says that, maybe in this case, our model isn't making that many predictions. It's missing a lot of predictions it should be making, but the ones that it makes, it's making very accurately. And oh, look here, if you look at our little confusion matrix, we can kind of see that here, right? So it's predicting a lot of healthy that should be healthy, right? But, and here, it's not predicting, let's see here. Yeah, there's only a handful of times when it's predicting, am I seeing this predicting? Is this? I'm not sure actually if this confusion matrix corresponds with this now that I'm looking at it. Because if the true thing is healthy and I'm generating sick. Oh, sorry. Sick is the label we're trying to predict for. So you got to read this the opposite way in this case. So in this case, if I am predicting sick and you actually are sick, so I'm getting things here. But here, as you can see, only 2 instances where I'm predicting sick and it's healthy. So very few false positives. But look, I have a number of false negatives here where I'm not predicting sick, but I should have been. And in fact, if you see that here, your recall score is comparatively much lower. In fact, it's almost 50% there, which says there are a ton of cases where the person is sick and I'm just failing to predict it. And then finally, the F1 score, again, just because, because there's a little bit of a class imbalance between healthy and sick, we have more healthy than we have sick. So my accuracy score is higher than my F1 score. But because of just how bad my recall is, it's weighing down my F1 score. And oh, by the way, this confusion matrix, how do you do it? Well, for project 2, you're given some sample code. You're given a sort of a nice function, this draw confusion matrix. That's one of the methods that we provide you. And then for this, you just like this, you just put in your actual label, your predicted label, and then you can put in your parameters for this. So in this case, healthy, sick, but then it'll label them. So that's how you would code these. As you can see, super, super easy, super trivial to generate those. But any questions on I guess, the coding of?
That definitely helped me.
The draw confusion matrix is you import it from sklearn.
No, that's something that we provide you. So you can get a confusion matrix as part of sklearn. It's just we don't like the formatting of it, so we included a separate formula. If you look at the workbook, one of the helper formulas we give you is this draw confusion matrix. That just helps with the coloring and it provides a little bit sort of a nicer output than the standard confusion matrix.
In project 2?
Project 2, correct. So you
Okay.
have that's code that's given to you. So you just call that method, input these parameters, and you're good to go.
All right, thanks.
Yeah, so Godfrey, you do have to manually input your labels for it.
What I meant is are you able to make are you able to label your axes in an opposite way, put the true label at the bottom and the predict label on the left?
That's a good question. So like you're asking true label, particularly like, can you change the orientation of it?
Exactly, yeah.
To be honest, I'm not sure. I haven't looked at the mechanics for how we did that. I mean, undoubtedly there's probably a way to do that, but I'm not sure. So I'm sure there is a way, but within the draw confusion matrix, that specific function, I think we have that sort of defined for you. Maybe if you just use the raw scikit-learn thing, you'll be able to change the orientation of it if you want it to produce it that way.
Okay, all right.
Yeah, great question. Any other questions? Okay, so. All right, perfect. Okay, so one last metric we have to talk about, and that is, okay, ROC curves. So before we get into an ROC curve, let me just kind of take a step back here and talk about what it is that your model is essentially doing. So just about every classification model does two kind of things. First, there is that learning step where we apply some kind of either transformation, manipulation. Your model learns some kind of pattern about your data in order to understand it. And then there is a separate decision function, right? Once it kind of has that pattern of how your data operates, there is then a separate sort of decision function that determines how to classify that data. And generally speaking, because right there some classifiers will work sort of in absolutes, but a lot of the time, just to be precise, a lot of the times your model will generate a set of predictions of probabilities. And in fact, for this ROC curve, you always generate a set of probabilities. So like a logistic classifier is a good example of this. The way a logistic classifier works is it essentially transforms what was like a linear function into it kind of at a very high level, because we'll cover logistic classifiers specifically at another class. But what it does is it transforms what had been sort of a linear regression model into a logistical model that compresses it down to a series of predictions, probabilities associated with the classification. And so for every data point, you have an associated, your output of that model is an associated probability of, in this case, like a positive label. So it's not necessarily a binary, this is label 1, label 0, but there's an associated probability of it being 1 or a 0. So then you have a decision function that has to determine where to draw that line. Is it 51% and you assign that label? Does it need to be 67%? Like where are you confident enough in sort of drawing your thing that you can say, okay, I feel good enough with this that, I'm going to assign this label. So are you guys kind of following that? So with every machine learning thing, there's that learning step. There's that thing where we do something to our data. We sort of generate a model of the data to understand it. And then based on that, there's that separate decision function that says, okay, I'm going to assign a label based on these thresholds. And specifically, if we're looking at this in a probabilistic step, let's say we assign a probability of a label to my data, to every data point. And then I have to decide where that cutoff is, where that threshold is for above this number, assign, let's say a 1, below the number, assign a 0. So if you have that frame of reference in mind, then the question is, okay, well, do we kind of have so one of the problems we've always had with our data is we have a good way of knowing about like how our model performs within the data set that we have. Right? We have the training, we have the testing, we're doing all those things to kind of get a sense for how well our data will generalize. But is there another way of thinking about our data that'll give us a sense of how it will perform globally? And the short answer is yes. And the way we can think about that is we can look at how cleanly our model has sliced the data. So in other words, if we're looking at this like as a set of predictions, whether or not a label is, let's just use positive and negative to make it easy. If we look at this model as generating a series of probabilities associated with a positive label, how cleanly is that divide between the actual positives and the actual negatives? With the idea that if it's done a really good job, if it's clean, like if it's nicely sort of stacked all the real positives up here at the higher probabilities and all the actual negatives down here at the lower probabilities, then that says that it'll probably do a pretty good job generalizing because it has that nice kind of clean break. So at a very high level, that's what an ROC curve is looking at. An ROC curve is trying to tell us is how cleanly has our model assigned probabilities between positives and negatives. So what does an ROC curve look like? It essentially looks at the true positive rate and the false positive rate. So the true positive rate, we've sort of already discussed. Your true positive rate is actually your recall. So remember, if this column here is the actual number of real world positives, and my little circle is the number that I've predicted. So my true positive rate is recall. It's this divided by this. False positive rate is the exact inverse. It's the number of false positives as it relates to the total universe of negatives. So the final thing that we're going to think about here. So let me just talk about the mechanics of this, right? So we have our learning model here. We have, we've plugged in all of our data. We've generated a series of probabilities associated with it. And then we have that decision threshold. So, at some point we may say it's 100%, 90%, 10%, whatever that percentage is. Now, let me ask you this, looking back here, if we start out at a very high threshold, if let's say we say it's got to be 90%, I have to be 90% confident that something is an actual positive for me to assign a label. What do you think this looks like here? Are we going to get a lot of positive predictions, a lot of negative predictions? Like, what does that look like when we have a very high threshold? Okay, yeah, so Dean in the chat, that's exactly right? If we start out with a very high threshold, we're only going to predict a very few number of those. Exactly, basically everything will default to negative because anything that's below a 90% confidence interval, I'm just going to assign it to be labeled. I'm only going to allow a very, very few in. So, and just quickly as an aside, if we think about going back to our measures, that's what precision looks like. When we talked about early on, when we said about how you can change the model for that, if you really care about something like precision, this is the kind of thing that you can manipulate. You can say, you know what, I'm going to change my decision threshold to make sure I'm super, super confident. I have 95% confidence, 90% confident, whatever that interval is. I'm only going to allow a few things there that I'm absolutely positive are going to be the case. So my precision score will be high, but my recall score will be incredibly low because I've only allowed in a few positives. So now let's say I begin to lower my threshold. Let's say if I go from 90 down to 80, down to 70, down to 60%. What do you think starts happening to this mix of things as I start lowering my my confidence interval? All right, I will tell you. So obviously, just in general, as you lower your confidence interval, you will start making a lot more guesses, just intuitively, right? As things become more and more, as you're taking a lower and lower threshold for that confidence interval, you will just start guessing more. So you're going to be guessing a lot more actual positives, but inevitably, as you get lower and lower and lower, you're going to start to guess wrong. You're going to get some false positives in there too, particularly the lower you go, right? When you start getting like 50%, 40%, at some point, you're going to just start guessing more and more and more. So the total number of guesses is going to go up. Hopefully you're going to be getting a lot more true positives, but inevitably you're going to start getting more false positives too. And then what happens when we go to 0? When we take our decision threshold all the way down to 0? What happens then? What does that look like then?
Would like everything would be classified? So we'd be getting every false negative that you could get, you would get.
Perfect. Yeah. So at that point, our circle, this circle here literally just starts growing until it encompasses my entire data set. So good news is my recall at some point is going to be 100%, because if I just guess everything as a positive, well, then I'm getting everything right? My recall goes to 100%. But the bad news is I also will go to 100% of my false positives too, right? As I go to 0, everything will do that. So generally speaking, that is what we're looking at here, right? So an ROC curve, and we're going to visualize that in a moment, but it essentially what you're plotting is you're saying, let me look at how many, what my true positive ratio is versus my false positive ratio is as I lower my decision threshold. So remember, I start off with a very high one. I only admit just like a handful of points. And there, in all probability, those are going to be actual positives. So my true positive rate will be great, but my overall recall will be terrible because I'm only letting a few in. Then as I lower my threshold, I'm going to sort of make more and more predictions. Hopefully, most of them are going to be true positives, but I'm going to inevitably start letting in some false positives. And then as I go lower, I'm going to get more and more true positives, but more and more of my false positives are going to creep in there. And then eventually, I'm going to have there's going to reach a point where I've gotten all my true positives, but maybe not all of my false positives yet. But then if I keep going lower, eventually I'm going to get all my false positives. So that's generally the trajectory we're going to look at. And it's that ratio that we're interested in. It is for every true positive that I admit in, how many false positives am I letting in? So that's fundamentally what you're looking at when you look at an ROC curve. So if you, and when you look at the quote unquote, the area under the curve. So let's look at sort of how that would look like in real life. So let's imagine, for instance, that you have we're going to look at 3 examples here. One example where my model has done an amazing job, a perfect job of assigning probabilities to my true positives and my true negatives. And essentially, in this case, everything above 50% is a true positive and everything below 50% is a true negative. So I have perfectly, in that case, is perfectly assigned probabilities. So in this case, this is, and so that's going to be the first thing we're going to look at. The second thing we're going to look at is a thing where it does a good job, but a little bit of a messy job. So here, the vast majority of the, if you're looking at, if this is your probability from 100% to 0%, here it's getting most of my true positives, but as I get close to 50%, it starts to get a little messy. Some of my false positives start creeping in here. Some of these, and then when you cross that 50% threshold, I also have some false negatives here. So there are some certain things that should have been labeled positive, but aren't. And so, below 50%, they're creeping in there, but then it's still doing a good job, right? There's still that kind of nice divider. And then finally, this is an example where my model is essentially doing nothing. It is just pure random chaos, where as I lower my threshold, I'm basically getting them in equal proportion. There's nothing, it's not doing any kind of work to actually classify. It's just pure flipping a coin, basically. So those are the 3 kind of examples we're going to look at here. For this curve, this is the plot that you're going to generate here. There's 2 axes. There's your true positive rate and your false positive rate. But there is a 3rd dimension that you don't see here. There's the z-axis coming out here, and that is your threshold, right? So there's going to be a plot point at a 1%, a 100% probability. Maybe there's one at a 99, 98, maybe, each thing down there. There's sort of off in the z-axis, there's that, but we're not seeing that here. What we are seeing here is the relative ratio of it. And it says for every kind of change in true positive, what am I seeing for true negative or for false positive? So in this case, I'm admitting more and more true positive, true positive, true positive, true positive, true positives, true positives up until that 0.5 ratio. But at this point, my true positive rate has gone to 1. So I've had total recall here before I've made a single false positive mistake. So it's a perfectly vertical line right there. Because all of my true positives have been admitted into my model by my decision threshold before I've admitted even a single false positive. And then here, and then just as my false positives, as my threshold continues to go down, my false positive ratio eventually goes to 1 as well. But again, it's been like a perfect separation. Here's the example where it gets a little messy. So here it goes nicely and vertically, right? Where I'm admitting a lot of true positive, true positive, true positives, but maybe right around at, let's say the 50% mark here, right around here, I start admitting some false positives. So suddenly my false positive still creeps up. Now it's still the vast majority of the ones I'm letting in are going to be true positives. It's still a very vertical line, but that number is steadily increasing. So the false positive ratio is going up. And then right around here, this inflection point here is pretty much right around here, where now the ratio starts to shift, where at this point, I've admitted most of my true positives, but there's still a handful left, right? So I'm at, let's say, like a 0.8, a 0.85 number of true positives. But at this point now, I'm admitting fewer and fewer true positives and more false positives. Until it eventually, at this point, I've pretty much admitted all of my true positives. And now at this point, I'm just finishing up my false positives. And then here, this is the worst possible scenario, where my model has done absolutely no work to classify. Everything is just pure statistical chaos. And here, for every true positive I'm admitting a false positive in equal proportion. So it's just a straight diagonal line. So I know that that's kind of a bit abstract, but that's generally what this is, what an ROC curve looks like and what you're looking at when you're seeing that ratio between true positives and false positives. So let me just pause there and see if you guys have any questions about that.
What happens if there's multiple classes?
Oh, good. Good question. You can still, with the multi-class, there's still a true positive and true negative, right? There's still that false positive and true positive thing. It's just in that case, right, because there's still you either got it right or you got it wrong. But there is a question of like, if you got it wrong, which thing did you predict otherwise? You would still generate an ROC curve for a multi-class classifier.
Okay, so it's just like everything that was wrong and everything that's right, and you mix that information all together?
Exactly right, yes. Yeah.
I have a question about the graphs on the left.
So these right here?
Yeah, what are the
Okay.
red and the green lines? Like,
Okay.
are there like positive and negative data points?
Yeah, great question. So in this case, your green is your true negatives. Your red in this case is your true positives. So and your x-axis here is the probability your model assigns to a positive label. So it's the idea that as you're going from 100% certainty down to 50% certainty down to 0% certainty. And it's the idea that like this, so this is an example where your model has assigned probabilities perfectly, where every true positive is assigned a probability greater than 50% of it being positive. And every true negative is assigned a probability of less than 50% of it actually being positive. So that's what this is. These graphs on the left are looking at here.
I see. Thank you.
Yeah, absolutely. Any other questions? And so the final thing to mention here is that there is a specific metric associated with these curves. I mean, obviously visualizing the curve is important, but there's a specific sort of calculable metric here called AUC, or area under the curve. And that is the idea that, right, if you have, this is a 0 to 1, right? So it's a 1-to-1 unit thing. So if you have a perfect ROC curve, your AUC is going to be 1. Then if you have sort of this worst curve here, your AUC is going to be a 0.5. So generally speaking, your plot will never be either extreme. It'll generally be something in this range, but you want to get something that is as close to 1 as possible. So conceptually, are you guys kind of feeling what an ROC curve is telling you and all that jazz?
Yeah.
Okay, cool. All right. So do I have, oh, then let me just jump ahead here. So here is, so just so you know, it's also pretty easy for us to generate ROC curves here. So you can, this is just some sample code that you can use for generating your thing. So here you put so you define your, so there's kind of an important thing that you're going to call here, which is going to be your ROC curve. Again, you import it as part of your metric thing. You define your false positive rates, your true positive rates, and your thresholds. So essentially you're doing a sort of a 3-dimensional matrix for this. And then again, you have your target, you put in your actual labels, score, which I have to tell you about. And then it's array position as your starting point. And then I think that's just a placeholder thing for that. But let me come back and tell you what score is specifically. And we're going to give you sample code specifically to handle that. And then from that, you just do a apply plot thing here. And so then you can, you just define the figure, you plot these two, you plot the ratio of these. So you're saying these are going to be your axes. You can define the title, you can define your X and Y labels, and then you just do the show method to generate it. But let me come back and tell you about score. So this is kind of an interesting thing that's specific to SVMs. I'm sorry, I should tell you what an SVM. So this is something we're going to talk about in a previous thing. But remember how I told you that we're looking here at statistical probabilities, that we generate a probability associated with these. Not all of your classifiers will do that. And in fact, some of your classifiers will not. And an SVM, or a support vector model, does not do that. What a support vector model does, and again, we'll get into this, but it generates it generates kind of a line or a hyperplane in your quadratic space. It literally, like if you're looking at your features as this n-dimensional space, it will literally sort of devise a quadratic equation that essentially slices your data plane into 2. And then it says everything above it is one label, everything below it is another label. And there's no kind of, there's a little bit of hand waving there because you get into some hard margin, soft margin stuff, but by and large, there's no statistical probability associated with it. It's wherever your label falls above or below that line is the class associated with it. So you need to generate probabilities associated with it. And so in general, so there's a specific step, and I'll show you that in next class, that you do for an SVM. But for SVMs in particular, one way we get around that is we'll actually generate multiple SVM models and just see for each model how it classifies a particular point. And then using that in aggregate, it associates a probability associated with it. But for all of your things in general, there's going to be this score thing here. And that gives you the probability associated with it. So in this case, what you're looking at here, so that score thing. So remember how for your other thing, you look at your predicted thing. Here, you're looking at your score, and that's the probability associated with that thing. So here is your actual label, and this score thing, which again, I'll show you the code to do that. It gives you your probability associated with a positive label. So that'll tell you if it's a true positive or a false positive. So any questions about that? I feel like I kind of threw a lot conceptually at you, but again, we will give you specific codes to handle all of those things.
Don't you use your score to make your predictions?
Yeah, so you do. So that's what you, so Chelsea, great question. So your score, right, going back to here, your score, there's that, remember there's that decision function here. So there's some model here that we first do to generate those probabilities. And then there's that separate decision function to give you your actual label. So like when we're looking at the rest of our metrics, that predicted array, that's the actual label we're generating. But what we're not seeing here is the underlying score, whatever that probability was associated with it. So the difference here is now we're looking at a score, and this score is going to be on an array from 0 to 1. So, and with that being the probability of you predicting a positive label versus what the actual label is. So your actual label is 1, your predicted score is 0.9. Your actual label is 0, your predicted label is 0.4. Your score is 0.4. So all you're looking at here again is looking at the probability associated with that. So that's what you're generating when you're generating the score thing. All right. So any questions about that? I guess additional questions about that? So, okay. Yeah. So question about why it's so jaggy. So good. And so Tommy, you're exactly right. Right. So remember the Z-axis, it's looking at a discrete set of thresholds. And you can actually manipulate, there are default number of, I forget what the default number is, but you can actually define how many thresholds you want. But yeah, so there's that, if this is your true positive rate, this is your false positive rate, there's that Z-axis, which is what the threshold is associated with it. So there's going to be 100%, let's say 90%, 80, 70, 60, whatever it is. And the idea being that as that probability threshold goes down, yes, your true positives continue to go up, but your false positives will also begin to increase the lower your threshold goes. So, okay. So we've kind of already talked about all these things, but I think this is kind of a nice summary about metrics of where to use. So general rules of thought. Accuracy. Accuracy is useful when we care about true positives and true negatives. And, we just care about like the overall performance of our model, particularly if we're looking at a balanced data set. Whereas we called out like saying F1 scores when you particularly care about false positives, false negatives, like those type 1, type 2 errors, and F1 scores may be the way to go. And, we said within that, precision and recall can be specific metrics if you really, really care about one of those edge cases. If you really care about not allowing for false positives or not falling for thing. Oh, there's a question in the chat really quickly about, can you use the plot ROC? Yeah, you totally can. Again, this is just a general rule for the course. We give you sample code, but you're not like bound to use it. You can use whatever alternative methods you want. As long as you're getting the result, you can absolutely use that. Yes. Yeah. And in fact, that's probably a lot easier than the method I have. In fact, I'm sure it is. So as we mentioned, in most sort of real life classification problem, because you have imbalanced classes, F1 scores tend to be better, particularly again, because they handle those class imbalances. Then we mentioned sort of how confusion matrices were useful for diagnosing the performance and just visualizing the types of errors you're making and where they're clustering. And then finally, ROC curves are a great indication of the generalizability of your model. Because again, if you have a model that's doing something like this, that bodes very well for it because it says it's doing a really, really good job sorting your data properly. And that says that it'll probably generalize very well. So, okay, we did all that. Okay, whew, that is a lot. Okay, so I want to do sort of a time check and everything like that. I have some slides here on cross-validation. Do we want to cover that, or do you want to just like call it a day and just open up for general questions? Or how are you guys feeling? Okay, I'm seeing 2 votes for cover. Any votes for don't cover it and let me eat my lunch? Okay, so you felt like it was covered pretty quickly in class. Oh, and by the way, just a quick reminder, and I hope you guys are sending me memes because time is almost up to do so. So if you haven't done it yet, I'm just going to quickly peek at my inbox.
I thought we'd find out the winner next week.
No, we're finding out this week. This is happening end of discussion. I'm literally gonna, like, the last 5 or 10 minutes of it will be, I'm gonna paste all them in and we're gonna vote on it. Okay, I'm seeing some submissions already coming in my inbox. Cool. Okay, you guys are awesome. So if you want to get it in, better get it done quickly. Okay, so then, all right, I'm seeing some votes to cover. So let's do this. Let's do cross-validation. So we talked about a little bit in previous discussions about train test split and what the problem with our train test split was. So if you recall, we have our data here, and then in order to kind of test its generalizability, we sort of segment out part of our data. We build our model with this, and then we apply that model to this data that it's never seen before to try and see how well it performs against data it's never seen before, right? That was essentially what our whole approach to training testing is. But then we talked about sort of the problems that you can get if you just do that train test split. And remember, we talked about, like, because this is just a random, dirty way of doing this, it puts your data at risk for biases. It just, whatever your distribution happens to be, whatever, however the cards just happen to have been shuffled that time, could significantly impact your performance. And we talked about, how just like you can see that yourself, like if you turn off random seeds and you just, run your model, you do a train test split, you do a train test split again, you'll see your model performance will vary just based on that. So we know that it's highly kind of, it's highly dependent on the specific data it's looking at. And then we already previously talked about an approach we could take to that. So if you guys remember stratified shuffle split, so we had that idea that said we could define, if we wanted to make sure that our data was proportionate along certain kind of features, we could do that. We could do a stratified shuffle split. You guys remember all that? We're good on that? I'm going to take that as a resounding yes. And then, but now we're going to talk about kind of another approach you could do, which is the idea of cross-validation. So here's the idea that says, you know what if, and I think this visualization is kind of a great way of thinking about this. What if instead of kind of doing this arbitrarily, where I just happen to randomly divide my data into training and testing cohorts, what if I do it systematically? What if I take, in this case, so the K, we seem to love using K as our default sort of variable for that. What if I define sort of K number of splits in my data, and then systematically train and test my model against each of these splits? So in this case, I train my model off this and test it, train my model off that and test it, train my model off that and test it, train my model off that and test it, and then finally train off that and test it. And then let me see how my model performs in each of these scenarios. So the idea here being saying, okay, well, how sensitive is my model going to be to the particular quirks of whatever subsampling of data I happen to have done with it. And that in general is the precise, I mean, that is exactly what you're doing with a cross-validation. You're essentially saying, rather than training my model once and getting the results once, let me systematically train my data against different kind of permutations, different cuts of my data, see how it performs in each of those, and let me see in aggregate how that performs, because that will give me a sense on how robustly my model is performing. Yeah, and these are the specific steps for it. So again, generally speaking, you want to shuffle your data set to induce randomness. You then will split it into K groups. For each group, again, you have your training and your testing cohort. You fit your data against your training cohort. You test it against that, and then you evaluate it, and then you sort of save that evaluation. Something important here is that, so here's kind of, I think something that when I first learned about cross-validation, I didn't really appreciate with this, is I thought that there was going to be some degree of transfer learning here, where it was the idea where I build a model here, test it, then I take that output, train against here, refine against here, and test it here. And then no, that's not what it's doing at all, because we don't want to feed in sort of data that we have previously trained on as a new testing data. What we're doing here is we're literally, so in this case, we're looking at a K of 5. We're literally defining 5 independent models. And that's kind of an important thing to understand here. There's no sort of transfer of knowledge across models. These are just completely independent models that you're training, you're testing, you're taking those metrics, and then you're aggregating those metrics. So, essentially the whole value of doing this though, is so remember, we said the problem with the train test split was that it was arbitrary and it was subject to those biases. The whole idea of doing a cross-validation is you're trying to kind of correct for those biases, or if not necessarily correct for it, see how sensitive your data is to those biases, I think is a better way of saying it. See how much your data can be skewed based on however the train test split happens to occur. And again, this is another, so a lot of things we're talking about here is like generalization, because if you recall, like taking the big step back here, we always have this problem where our data is this snapshot of the broader universe, and we're always trying to figure out how well that data maps to that broader universe, or how much of that data is sort of biased, or there's kind of variance or statistical oddities within that sampling that I have that aren't really reflective globally. And so by doing this cross-validation, it gives us a sense of that robustness. It gives us a sense of how much our data, how much sort of noise in our data can throw off our prediction depending on how it happens. So do I
So in regards to this, I'm assuming, is there a function that like does that and you plug in a K value and it splits your data automatically, or do we have to like manually go and make sure that like our data segments aren't overlapping and like kind of create buckets?
Yeah, great question. Okay, so there is, and for some reason I didn't prepare a slide on it, but yeah, the short answer is there is definitely code for you, and I will just pull that code up so I can just show you, because I should have had that ready for you. So if you guys give me a second, I will. Okay, sorry guys, give me just a moment. Where is my project 2? Okay, sorry guys, I have to figure out where I put my directory. Okay, here it is. Okay, so I will show you a couple things actually that I should have showed you earlier, but I didn't. Okay, so two things I want to show you. Okay, so the first thing is, so I mentioned getting your score. So that is a different, so let's just look at this k-nearest neighbor algorithm here. So, so you're predicting, remember this part you've already seen. That's where you call the predict method on your data. That's where you get your output. And then the next thing, actually, let me not show you that one particularly, because that one's not as great for our purposes. Okay, so let's look at for this one here. So in this case, we get our predicted, which again, we just call on our testing data, we get the series of predicted labels. Then this is the score thing. There's a separate method called predict proba, which is sort for predict probability. And again, here you can generate your array that gives you the probabilistic score associated with a positive label. So when you're looking at your ROC curve here, that score that you're going to generate is just simply going to be that predict probability thing. So rather than generating so if you just do the predict method, you get your actual labels. Your predict proba gives you the underlying probability associated with that label. And so, and again, that's all you need here is your actual label and the probability associated with that, and it'll generate your ROC curve. Okay, then let's look at, okay, so then let's look at how you would do a cross-validation. So like your, you can, so from scikit-learn, they have a model selection, you can import k-fold. Then you define your specific instance of it. So you define k-fold equals model selection, you're doing k-fold. Then you do n split. So that's the number of times you're splitting your data. And so in this case, I'm going to define it as 10. I'm going to do a random state. So that's my seed. In this case, I'm going to do 42. Pop quiz. Any reason why I'm doing 42?
Because it's the meaning of the universe or something like that.
That is literally why. Yes. Yes. The answer to everything is 42. And finally, shuffle set to true, because before doing it, I would shuffle true. Then once I define my specific model, this is just like I was doing my regular thing. So in this case, a logistic regression. You don't have to worry about those specific parameters. You'll go through those later. And then my results are, I call model selection, my cross-validation score, which outputs, in this case, it's going to be my results. So in this case, I'm pulling my accuracy and getting the results for that. My model, which I've defined here, train, target, and my cross-validation method is k-fold, which I've defined here. So I just define all those things, and then it just outputs my results. And here I'm going to take the mean of my accuracy, and then it just gives me, in this case, this is the average accuracy across all of my folds. So that's what you would do. That's the code that you would run to get to do your cross-validation. So yeah, any questions on that?
So the cross-validation, since you're getting this mean accuracy across all these folds, is it basically just saying what the expected average accuracy is for that model, but it doesn't actually do anything to make the model better, like
yes,
in and of itself? Okay.
Yeah, that is exactly what it's doing. A cross-validation will not improve your model performance at all. It'll just say if I have, in that case, if I have randomly split my data 10 times and train those models, on average, my performance across all of those models will average out to be that. And within that, there's a lot that you can look at there. You can look at your distributions, you can look at your your min maxes, you can look at, right? There's a lot that you can look at with that. But those are just that's just one of the things that you can output from there. What is your average performance across in this case, 10 randomly trained models.
Okay,
So
cool. Thanks.
yeah,
So-
absolutely.
The model for like your next like input, which model do you use?
Model for my, sorry, for my next, what do you mean by that, Chelsea?
Like if you used your model to classify something new,
Mhm.
which model would you use? Because now don't you have 5 different, or you have K models for a K fold, right? So you trained K models.
So, are you, so let me go back to let me just share my screen again. So if we're looking here, so you're asking, so again, here we're just defining our specific sort of parameters for my K-fold. So I'm defining within model selection K-fold. I'm going to say I'm going to essentially do 10 models. I'm going to split my data 10 times, defining the parameters for that. The specific model I'm going to use each time is logistic regression. So each time I'm going to use a logistic regression, and I'm going to define my output for that, which is just simply model selection, my cross-validation score, which is I'm going to output the scores for it, the model, which I've defined, my training and targeting data, and then my cross-validation strategy, which is this K-fold parameter, which I've defined here. So you're asking if we change up the model, like if we want to not do a logistic regression, if we want to do, let's say, a SVM or a Bayesian or a random forest, is that what you're asking?
No, I think Daniel answered my question in the chat. Like,
Oh, okay.
if we're using the model for something else, like new data, then you would like pick one of them because you trained it like 5 different times or whatever. So
Oh, yeah. So your question is like, if you've trained it 10 times and let's say you're happy with the performance, which one do you take?
yeah.
Yeah. Okay. So then you would, it's a good question. I'm not actually sure how you would output the specific model. I in that case, what I would probably just do is I would just run it independently, not using my cross validation, and just take that, export that model. Because now once that gives you an indication of its overall performance, and you can say, okay, well then I can, with a certain degree of confidence, expect this performance, then I can, train it with a certain random seed and just take that thing. But I don't want to say for sure there's no way to output that, because there probably is. I just haven't used cross-validation in that way. Like maybe you could export the highest performing model within your cross-validation and say, I want to use that one. But I haven't used it that way, but so I'm not sure if you can.
Okay.
So I know it is late, but we have memes to digest. So let me populate our spreadsheet with those. And while I'm doing that, let me just open up and see if anyone has any questions more generally. Let's see, who do I got here? Okay. Oh, Sammy, that's harsh, man. You're just covering up my face. Okay, so it's, let me make sure I got the right name. Okay, so that is one. And by the way, I'm typing out these names super quickly, so if I make any mistakes, I apologize. Okay, so we got Sammy, we got Neil. Well, some of these are great, I can tell you already. Nobody's got any questions?
We're trying to meme.
Okay, so Tammy, I'm just gonna paste your caption, okay, into a slide so people can vote on it, okay?
I don't have the graphic design skills to actually put it on an image. I'm sorry.
So it still counts, okay. All right, so there. And who was it, by the way, who recommended I pre-populate a poll with like lettered options? Because we're doing that this week, which I think is brilliant. Okay, and then oh, Michelle, I got either way worked. I got it either way. Okay, so it looks like we have 4 entrants. Okay, let me just make sure I didn't miss anybody. Four. Yeah, okay, cool. All right, let's do this. Share, present, and sharing screen and presentation. Okay, so first entry, who also, by the way, so we're going to do polling in a moment, and you're going to put in a number. So our first entrant is going to be Sammy. So he is going to be entrant A. So here's his meme. Me having fun on the weekend. Also me realizing my assignment is overdue. That is pretty funny. So Neil, entrant B. Dad won't let me eat those sticks. Okay, so Tammy, this is going to be the caption. Realization hits, you're going to. And finally, D. Okay, that's awesome, guys. So again, from the top, we got A, B, C, and D. And I'm going to officially launch the poll. Are you guys able to see these results? Like if I'm sharing my screen, can you see this?
No, you have to
Not yet.
share the results like manually. Because
Oh, okay.
we can't see like your like Zoom like stuff.
Oh, my okay. Gotcha.
Yeah.
Okay, it looks like 80% of you have voted so far. 82 have voted. I'm gonna let go for another 10 seconds. By the way, that DJ Little Boba send you off into the weekend. Okay, 89% have voted. 92. Gonna cut it off. 5, 4, 3, 2, 1. Okay. Share results. Our winner in a landslide is D. Michelle, let me go back here. Boom. Trying to pay attention and lecture with the video on, thinking about what to stress eat after. That is glorious. Well, Michelle, take a victory lap. And Michelle, send me your preferred email. Or can I just use the email that you sent me? Okay, perfect. All right, I'm gonna stop.
Wait, Lionel, did you just like not get mine?
Oh, wait, who's?
I like.
Oh no, did we miss one?
Me. Like it's fine. I was just wondering where it
Kesha,
went.
no, hang on, let me look. Uh-oh, I hope I didn't. No, I don't see it.
Yeah, I sent one also, but I don't care that mine was skipped. Mine was poopy.
Keshav, I don't. Oh, wait a sec. I do see yours. No, Keshav, I missed yours. It did show up.
Rip.
Okay, hang on. All right, you're gonna get a bonus prize then. I'm sorry, but I'm gonna share screen so everyone can see this. I'm sorry. I did pray. Okay, this is Keshav's. Hateable. You went after our old glory. You went after Bolter. That was solid, man. Okay, you know what? You're gonna get a bonus prize too because I deprived you.
All right,
That's a pretty good one too.
That was solid. Okay, all right. I'm gonna stop the recording.